Okay, so we had gotten up to question 4. We'd finished up till C triple I. Good news is we can actually kick back off from where we left off because it did then swap to another probability type. So it's pretty typical that none of the previous stuff is going to matter too much when a probability type changes. But if it does, we'll obviously go back and have a look at that. So I feel like we should reasonably be able to kick off back at DI with question 4. Let's see how we go. Large random sample, approximate 95% confidence interval, and the result of that confidence interval is actually given to us. And we're required to figure out what sample proportion, so p hat, was used in that calculation.
Chris, I'm gonna need your help on this one.
Yep. I don't think you might not need too much. So first we'll pop up the formula sheet. This is how you calculate an approximate confidence interval. So you got p hat minus the z root and p hat plus the z root. That's how it's calculated. What we want to know is p hat specifically. And so if we're trying to calculate p hat, we actually already know the upper and lower bound. We're given them. So if we have a look back at the beginning, here. So lower bound is 0.102, upper bound is 0.145. So we're given what those things are. That's what the entire left hand and the entire right hand side are, the upper and lower. There's a really easy way to calculate p hat from here. Any ideas coming to mind based on what I've just discussed so far? As you think, I'll also draw a little bit of a demo. The upper is p hat plus something, the lower is p hat minus something. Fill in the actual values from the question. 0.102, 0.145. And we want this p hat. Important thing to note is the thing that you're plussing and minusing are the exact same thing. So maybe another hint would be, instead of thinking about it as like z root a whole bunch of stuff, let's just say it was 2. If I knew this spot here was p hat plus 2, and this spot here was p hat minus 2, how might I get p hat? Now, obviously, these below numbers aren't going to work out for this. It was just a random sub in. But now I'll draw that. Try and draw it a bit better. Give it like 10 more seconds. I don't think I can do much more than that.
Do we just look in the middle?
I'm in the middle. That's it. Yeah. So you got p hat plus something, p hat minus something, p hat's the dead center of those values. So that's how you always calculate your p hat if you're given a confidence interval. So midpoint equation, 0.145 plus 0.102 divided by 2. 0.102 plus 0.145 over 2, and you can give it as decimal, you can give it as fraction, either way. They're both closed form. There's no like rounding going on in there. You'll typically see if it's given stuff to you as decimals, you would typically give it as decimals back, but it's not wrong to give a fraction. Fair enough then?
Yeah.
Yeah, it's one of those questions where once you know it, it's like, oh, obviously, super easy. Midpoint equation, very chill. You just got to know conceptually what's being asked, what are the key variables that we have access to, and then, yeah, just plug and play. This one will be a bit trickier, probably. Explain why this confidence interval suggests that the proportion of adults with a slow heart rate could be different to the proportion in Massland. Okay, so we will need to care about some other stuff. So we know this one, 0.102 to 0.145, basically just says that we are 95% confident that the proportion of people who have a slow heart rate is going to be somewhere between like 10% and 15%-ish. You know, just doing a bit of rounding there for the explanation. So we know the proportion is going to be somewhere between that. We're supposed to be comparing that to the Massland proportion, which was back over here. So let's see. How far do we need to go back for that? Yeah, okay, here we go. Here are some basic stats for the Massland stuff. So it's got a mean of 68. Oh, hang on. No. We need to know what slow heart rate means. There we go. Probability of a randomly chosen Massland adult with a slow heart rate is 0.158. So that's effectively, you know, if we're now looking at what is effectively a massive sample size, we're able to then say, cool, whatever the average of that sample size is the proportion. So Massland has 0.1587 as its proportion, and we have a confidence interval for where the proportion is likely to be for Statsville, and that's from 0.1 to 0.145. Why does that suggest it could be different? I've got all the numbers down on the same screen now. Without even really thinking about the background information there and just looking at the raw numbers, what tells you that the proportions could be different? Because for this group, we're saying the proportion is somewhere between that lower and that upper. And for this group, we're saying the proportion is exactly this. What is it about those two results that explain why they might be, or that explains why the proportions have to be different from each other?
Is it because the Massline proportion is not inside the confidence interval?
Yeah, that'll be the most direct way of saying it. This one does not even exist in the interval to begin with. So there's no, I mean, sure, we're 95% confident, so yes, there's a 5% tolerance of error there, so yeah, maybe, but we're not saying for certain. We're saying it's suggesting that it could be different. That'll be the main thing to say. Yeah, in fact, that's probably exactly what the wording was for what they use in the exam report. Let's have a look. DII. Yeah, does not contain the Massland proportion. 11%, by the way. So, you know, if you guys are struggling with it and still more or less getting to it, as long as I'm giving some hints along the way, once you get it, like, you'll be fine. Because now, I mean, that would put you in top 11% if you're able to now get these questions easily from here. Even this one, like here, all you have to do is do a midpoint, and it's a 45% pass rate. But I'd hazard a guess that if you see a question like that again, you'll probably get it immediately, especially if I show it to you within like a week or so, I'd imagine. So as long as we're learning from these things, even if we're getting them wrong to begin with, you'll recognize the question again and be able to solve it from there. But okay. Next up. Every year at Massland, students hike to the top of a hill. The time it takes to do that is given by this probability density function. Find the expected time in minutes for that to happen. Expected time, expected value, these are the same. Yeah, same sort of thing. One of the things we have to do is figure out what kind of probability we're up to now. Piecewise pretty much always means only one type of probability. That probability type being continuous. So it means that when we start looking for support from a bound reference or the formula sheet, we'll look at purely the continuous stuff. Expected time, expected value. Another keyword for that would be the mean, right? Expected value and mean are talking about the exact same concept. Let's see, on the formula sheet, do we have a thing for continuous? We do, yes. So mean, continuous, there. We're solving that integral. How are we going to apply that? So it's integral from negative infinity x f of x. We now then have a look back at what we've got. We've got our f of x, denoted as m of t. We've got a domain of t greater than or equal to 0. How are we going to apply that equation? What are we going to actually write? I can say we're definitely going to start with the integral. And x f of x, that's definitely going to happen. All right, so just chucking those in, x times function. Only thing is the negative infinity to infinity. We're not going to quite do that. What are we going to do instead?
It's going to be 0 to infinity.
Exactly, yeah. Because when we do an integral, we're doing it over a particular domain. And the reason why it says negative infinity to positive infinity simply just means we're trying to integrate over whatever the maximal domain of that thing is. And so because we're doing from 0 to infinity as our actual domain given to us, then we're going to put that as our integral boundaries. It does say give your answer to one decimal place, so I'm not overly concerned about the fact that it gave me that back because we can just control enter on it, or otherwise convert to decimal and get our 44.6 as our final answer for that one.
Chris, where can we put infinity from, like in the CAD?
So that's in the pi menu. So if you're using this CAS, it's the pi one. And for the other one,
Yeah, got you.
yeah, I'm curious. What's the other one? Where's this going to be? It'd be good to have this for the recording. Let's see. I don't actually know where this one might be. It's infinity for this. I mean, I'll keep having a look for that. In the meanwhile, as long as all that makes sense, move on to part F. Where is this infinity? Oh, it's right there. I saw it. Math 2. Students who take less than 15 minutes to get the top are considered elite. Find the probability of being elite. Okay. Worth noting for continuous probability, whenever we're trying to find probabilities, we're always doing integrals. Because the reason why is because area under a graph is considered probability when it comes to continuous probability. So we're saying less than 15 minutes means elite. So probability of being elite is actually the same thing as probability less than 15 minutes. That in mind.
Do we integrate from 0 to 15 and then put it over like the total?
Integrate from 0 to 15 and put over total. How do you mean total?
Like the answer we just got before.
This, this expected value here.
Yeah.
So the expected value just tells you what's the mean of the scenario. So what's the average time it takes someone to get to the top of the hill or whatever it was. In this case, we're just trying to do less than 15 minutes. The only time we would put it over a new denominator is under conditional probability circumstances. So, for instance, if it was less than 15 minutes given less than mean, then you might start using stuff like that, where you change the denominator up a little bit. But yeah, in this case, it's a fairly standalone question. It's just, what's the probability of being less than 15 minutes? Well, it'll just be the integral from 0 to 15. Cool. Okay, that's that. Yeah, here we go. This may or may not be conditional, actually. Let's find out. Part G. Year 12 students make up a seventh of the total number of students. Of the Year 12 students, 5% are categorized as elite. That's a special wording there. Of the Year 12, 5% are considered elite. Find the probability that a random non-Year 12 is elite. 2 marks, so there's going to be a few complications to worry about. Very tough question, apparently, as well. 6% got 1 mark and 5% got 2 marks. Another hint would be that the previous answer is going to matter, because we got the probability of any student being elite. We've calculated that one. This one, we're specifically looking for a non-year 12. We're not going to get this all in one go. Um, one of the things we might want to do would be to set up our like a maybe a tree diagram sort of thing. So we can say, okay, there's two things we're looking at. It's year 12s and non-year 12s, and it's elite versus non-elite. So those are the things we're contrasting. You can do a tree diagram, you can do a K-map, the probability table. Doesn't really matter which way you go. It's probably slightly more effective to work off of a probably slightly more effective to work off of a tree diagram because there's a sequence involved in there that's somewhat natural, which would be you've got your probability being year 12 and not year 12. That'd be the first thing you check. Year 12, my 12 dash. And then from there, they're either elite or non-elite. We can start filling out a few of these things. Like for instance, year 12s are a seventh of the total number of students. So this will be 1 out of 7. And of those, 5% are elite. So you could do 5 over 100, 1 over 20, 0.05, however you want to write that probability. And we want to find the probability that a non-year 12 is elite. So that spot there. That's a non-year 12. And we want to find the probability of them being elite. Based on what we're looking at from this tree diagram, what are things we can start putting in place? There's some things we can fill out, even by just ignoring the question and focusing purely on the tree diagram. There are some spots in there we can fill out.
The amount of non-year 12s and
Yeah,
non-elite year 12s.
for sure. Yeah. What are those numbers going to be?
6 over 7 and 0.95 or 9 to 120.
Yep. Yep. Both of those work. Cool. So that's about as filled as this tree diagram is going to get now. We don't have enough information to do anything here, at least not yet. The other thing that I said was going to be important here was the probability we calculated earlier, which was a probability of any of them being considered elite, is going to be whatever that number was before. So that 0.0266. So I'll write that over here. 0.02, yeah, 266. This is the probability of anyone being elite. So if I just said find the probability of elite, and I didn't show you that number, what would be the things you do in this tree diagram to find the probability of elite? You know what, we have the number for it. And let's just say these are filled out. This is, I don't know, 0.2. This is 0.8. If I say find the probability of elite with just this information from the tree diagram, what do you do?
You multiply like the branches for elite and then you add the probabilities.
Absolutely. So in this case, it'd be 1 over 7 times 0.05. 1 over 7 times, we'll probably use fractions at this point for that. And then you'd add that to 6 over 7 times 0.2. But in this case, we're going to just leave that as x, as some unknown. And that would equal the probability of being elite, which we actually have a number for. Suddenly, we have an equation with just one variable in it. This is now just a CAS solve. So let me copy that down. Now, obviously, don't use the rounded version, use this in its entirety when you do it. It may or may not matter too much considering no 4 decimal places. We're probably in the realm of maybe doing an error based on rounding. So making sure we use the full number. Oops. 1/7 times, we can even use 0.05 there. Why not?
Is the answer 0.0227?
0.0227. Yeah, that does come out to be that. Nice. And yeah, was that just the CAS solve like we talked about?
Yeah, first I done like the integral from 0 to 15 times 6 on 7. And I got 0.228, which is a little bit off.
Sorry, integral from where to where, sorry?
0 to 15 for the function, and I multiplied it by 6 over 7.
Oh yeah. Yeah, yeah. So
And I
that's what
didn't what
that's what they actually mentioned in the exam report. A common incorrect answer was doing just that. And do you know why that's incorrect now? Like, what's slightly
is it
off
because
about
of
that?
the 1 on 140 that we're missing?
Yeah, so it's because if you're just doing that, it's kind of like going back to saying, hey, if you just had this information, how would you get elite? You're missing exactly the whatever this comes out. Yeah, that's right. Yeah, 1 on 140. Yeah, so I'm missing that portion of it, which is the obvious answer, right? Like you see this equation, you compare it to this one. Yeah, obviously we're missing that. But I guess more importantly, it's because we're missing that set of branches that gives us more of a conceptual reason why, rather than just, hey, these are the numbers that weren't in the equation. Yeah, so probably tree diagrams would be the best way to do that. Yes, there's a K-map version of that where you could do year 12, year 12 dash, E dash, and then do your intersections. But the information that's provided to us isn't lending itself nicely to intersections. They're conditional probabilities. Um, Whenever it's something conditional based off of something, like in this case it was of the year 12 students, so it's a restricted sample size. It's a conditional probability. Um, if you did want to use K-maps, you'd have to go out of your way to do it. Like for instance, this right here would be probability of E given year 12, and that's your 0.05, which you can then expand out to be the intersection divided by year 12, which you can solve for the intersection, but you're adding a whole other equation in there just to get an intersection, which you probably don't want to do. And that's the probability section. Awesome. Anything further to clarify, let me know. Otherwise, we can start working on question 5. Back to some functions relation stuff, maybe even a bit of calculus, actually. A function, one's a quadratic, one's a linear. Find the coordinates of the local max of f. Oh, sorry, one's a cubic, actually. That's x squared times something with x in it. Yeah, I was going to say positive quadratic and a maximum. Didn't seem to make much sense. It's a cubic. Find coordinates local max of f. So finding local max, local min, there's one standard procedure for doing that, tech free, and there's 2, maybe 3 ways of doing it, tech active. the CAS has a function that will solve this mostly immediately. There's one further step you have to do if you're doing a TI Inspire. If you're Casio, though, it can give you the whole thing in one go. Otherwise, you have to do the tech-free method. Anyone getting close to an answer? Okay. So tech active, there's a function that'll help us out immediately. That's going to be the fmin and fmax functions. We're looking for a maximum specifically, so we're going to use fmax. This exists both TI Inspire and Casio. The Casio actually has a slightly better fmax because when you do fmax on the Casio, you get both the x and the y off of it. Whereas if you do it on the TI Inspire, like I'm about to show, you only get the x off of it. That's unfortunate. Why to do that? Do I need to give a domain? A greater than 0. What? 81x squared times bracket a minus x for a4 f max. Oh, right, because f max is going to give the global, and I haven't, yeah, because it's in terms of a, it's always just going to shoot to infinity. Yeah, okay, never mind. That works when you can restrict the domain, so forget what I just said there. We're going to have to default to the way we'd do it in a tech-free, which would be solving for derivative equals 0. And the reason why is because local max, local min, inflection point, those are all stationary points. So you would do a CAS solve, derivative of function is equal to 0. Two options there. From that, you're going to have to figure out which of those is the max and which of those is the min. It is a cubic, after all. We would expect to have, if it has two stationary points, one is going to be max, one is going to be min. Before I give that fully away, does anyone have any idea how you'd figure out which one's which?
I mean, you can put into the graphing tool, which reveals that one of the turning points is at the origin. So
yeah, so if you put it in the graphing tool, set a to be whatever, doesn't really matter. Because x equals 0 is a constant, you'll know for certain that the 0 is what would you say it was, sorry? A min or a max?
I mean, if you don't like change, if you keep a at 1, then
Yeah.
it's going to be at the origin, the turning point. So the 0 turning point.
Is it a min or a max though?
It's a min.
It's a min, yeah, okay. So we're looking for the max. Even if you were to change what a was, I imagine it would stay as a min on there. You can only choose positive numbers, by the way. If you go for negative a, then you're going to flip it, and that'll make it a max probably. But anyway, so we know that the 2a over 3 is going to be the max based off of that. The other way to do it would be double derivative. So you could do derivative of derivative, which is starting to get a bit weird. Derivative of f of x, and then shove in 2a over 3 into that spot, and see, hey, did we get a negative or positive result? And in this case, because we know that a has to be a positive number, positive cube gets you a positive, negative divided by positive is still going to be negative. So negative double derivative does mean a local max. And the final way to do it, which is probably the quickest, would be to just know what a negative cubic looks like. A negative cubic will always start top left and bottom right. So if it has two stationary points, and it's always going to do that, the max will always be after the sorry, what am I? Yeah, what did I have there? Hang on. Yeah, the max will always be after the min. I had a mind blank there. I thought we were trying to find a min for a second. I was like, hang on a minute. Yeah, the max will always be after a min when it's a negative cubic. So yeah, a bunch of ways you could figure out which one of those is which. Now just remember, we only found the x value there. So we're just going to get that corresponding y value by shoving 2a on 3 into the original graph. F of 2a on 3 gives us 3 on a for that final coordinate, or the y value of that coordinate. Any questions? And that's still a fairly low pass rate. That's a 50% one when all you're doing is finding the coordinates of a stationary point, fundamentally. Yes, Fmax / Fmin kind of broke a little bit there because we couldn't restrict the domain in a reasonable enough way. But otherwise, you should have a default way of doing that. If at minimum you would have the derivative equals 0 because you have to do that for tech-free. Part B. Find all the x values for the points of intersection between f and h. That should be chill. Points of intersection between functions. We've been doing that since linear.
Zero, 1 on 3, or 2 on 3.
Yes, you've done the right method.
Oh, it's
Why
got to
have you got?
sub them, right?
Say again.
Do we have to sub them back into the function for a?
Well, no, because you want to only find x values. But you are still, yes, so you did get some x values there, but they're not in terms of a. This is something you've done on your CAS to make it break a little bit.
When I do solve, do I have to do comma a?
No, so you did everything right. There's one thing you did before solving this question that's eliminated a from your solutions. You mentioned it when you were describing how to solve part A.
Is it because I put it on a graphing tool with the slider?
Yes, slider. So A has been set to 1, which is why you've got a third and, what was it, the third and 2/3, I think. So you're not going to be able to debug that in the real thing because you will go into circumstances where you will have to use a slider for certain things. Like flat out, you will just need to. There's no algebra to be done. And if you then go back into a question and you start getting numerical answers, you'll need to figure out, hey, why have I not got what I've expected here? And so, yeah, I can see if you had a equals 1, you would have got the 1/3, 2/3, and 0. Which actually, I just noticed in the exam report, a lot of people did that. So they would have used the slider. That's funny. Nice. So you're not alone. It's a common mistake to make. I don't really know how they would have gotten this, though. They do diff equals 0, maybe? Because that would be quadratic formula type stuff. Yeah, anyway. Oh! No, it's because they use 4a. Oh, that's sad. They didn't have the right denominator. Anyway. So yeah, as for just for the recording, how does that actually work? Any points of intersection between functions is always just going to be function 1 equals function 2. That's all we're ever doing. Part C. What is the total area bound by f and h? Okay. So area bound, there's a lot going on with that. This is where having that graph can be kind of nice, actually. Even if you don't ultimately end up using Well, actually, there is a good point here. One thing that's worth highlighting ahead of time is this doesn't say find total area in terms of A. So in other words, I'm reasonably certain A is going to cancel out. So even if you did leave A as a defined thing, I imagine it's not going to actually impact the solution. So this one's pretty safe to chuck into the graphing tool. So we're trying to find bound area between F and H. Getting those graphs going would be a good idea. Shouldn't matter what A is as long as you leave it as positive. Simply because we're told in the question it has to stay positive. In fact, to say positive real, not positive integer. Okay, got the graphs. Now just to restrict the window size, something a bit more reasonable. Let's say -1 to 3. The height on those seems okay to me. Yeah, we're starting to see it. So for bound area, we're just looking for when the shapes combine to make a perimeter. And so in this case, it's going to be between 0 and whatever this other spot is, int. And we can see, not too great though. How do I have to restrict this further? We'll go -0.5 to 2. Shrink this to -1. It's a bit better. You can see how the bound area is going to be contained in these sort of like little circular bits in here. We want to figure out what's this and this combined. So from there, once we've got a look at what the graph is going to end up being, we now need to figure out what are we going to do to solve area bound. It's a standard procedure.
We're going to set up two integrals.
Yeah, yeah,
I
two
think
integrals.
one of them will be like h of x minus f of x from 0 to a on 3.
Yeah, yeah,
And the other one will be f of x minus h of x from a on 3 to 2a on 3.
yeah. That's going to be it. So in other words, you're doing a top take bottom. You're saying that the linear is above the cubic for 0 to, this would be the a on 3, and then another one where you've got a on 3 to this spot over here, 2a on 3, where the cubic f is above the linear h. So you do f take h for that one. Yeah, that's precisely it. Those two integrals. You would use the a's to be super safe, just so I can see out of curiosity if I do leave my slider on like that. I'm fairly certain we'll get the same answer either way. But obviously you'll, in fact, yeah, I could even put the a on 3 since a is defined. It'll just sort itself out maybe. Not a good habit to have, but just in this one case, just for the exploration. If I got those the right way around. Yeah, h is linear, so that should work out. Yeah. Yeah, so 1 over a is what you're going to end up getting, whether or not you have a defined in the as a slider or not. Like for instance, if I print a, I have 1. If I then go and delete a and then redo this, it's still going to get me 1 over 8. Don't rely on that, obviously, but I just wanted to highlight the context clues in the question, you can derive maybe a bit more insight into the question than the examiners were intending. So it can help you. Yeah, so it can help you out.
Chris, on like the CAS we have on the graphing tool, we have this bounded area function
Yeah.
tool. Would that work here or
Um, it'll give you a decimal, and since we don't have decimal places in the question, we're not allowed to. I mean, we might see the decimal and know what that fraction's going to be, but there's no way of converting this stuff into fraction form. And so yes, it'll give you an answer to look at. You can be like, yeah, I know I want this decimal, so when I do my integral and control enter on it, if I get that decimal, I've definitely done it the right way. So it'll be more of a validation thing rather than your first point of call. Only use it as your main method of solving if you have decimal places allowed. Yeah, it's a really good thing. It's also slightly tricky because sometimes you click where you think there's an intercept, but you click slightly off of it. It's usually decent enough at snapping to intercepts because that's the whole point of bound area. But I have missed it before. Okay, here we go. New function G defined over a particular domain. Part D is basically nothing. You've got function G of X, evaluate what this is going to look like. It's literally just plug exactly that verbatim into the CAS. There's really not much to talk about for that one. Yeah, that's chill. Just plug in, get answer. And still, whether or not you believe it, 64% of people were able to achieve that. I imagine it was mostly because it's 5D, so you probably look at question 5, look at those harder questions, and probably just skip entirely and go to something new. I imagine that's kind of why there is significant. Whoops, can't go that far down. Why there is significantly less people solving what would otherwise be trivial. But that is kind of funny to see. 64% for something you just plug directly into CAS. Where it gets decently harder is going to be part E. Find area bound by G inverse, x-axis, and the line G of 2A over 3. Yeah. Okay. Part D isn't there randomly. Something about that. Hmm. You probably can. Nah, getting the inverse via CAS is probably a bit tough. Because cubic into cube root might work. Yeah, actually, before I draw this, let's just see if the CAS can give us inverse. Probably not a great way of going about it, but let's find out. X equals g of y. Oops, g of y. Y. Yeah, that's crashing. Yeah, inverse acquired. I'm kind of curious if you define that Are we going to get a good thing? Oh, there's also two things in there. Yeah. Okay. So, better than that is probably to try and get an idea of what we're actually dealing with. So, g of x is some negative cubic. It's actually the same graph as f. It's the exact same equation, just with a different domain. It's restricted, 0 to 2a on 3, which we may or may not remember. 2a on 3 was the coordinate of the local max. I think that's what that was, yeah. Yeah, local max. So when we draw out what that's got to look like, we had it turn at 0, and turn again. Whatever this was 2a on 3, so all of this is sort of irrelevant. And furthermore, since it's at 0, all of this is also irrelevant. So in other words, we're just doing this. That's g. Now, for g inverse, I'm going to draw our line y equals x. And then flip. So basically, it doesn't need to be perfectly accurate, but all of, well, maybe a bit better than that. But all of the concave down now becomes concave up, and all the concave up now becomes concave down. So that gets us g inverse. And you can put this on a cas with some value of a, right? I'm just sort of drawing it. In fact, I don't really know why I'm not doing it on the cas. Probably better to do it that way. So there was that. We got g inverse. Find the area bound by g inverse, the x-axis, so this bit, and the line x equals g of 2a on 3. So g of 2a on 3, I'll just do that slightly off camera. 2a on 3. That was, in fact, we already had that answer. All right, 3 over a. That was the turning point. So that's x is equal to that, which means 3 on a compared to 2a on 3. That is kind of cheeky, actually. What's bigger? 3 on a has got to be earlier, right? Because if you have a equals 1, you have... No, it's further. It can be further. If a is 1, you've got 3 on 1, so 3. That's weird. You almost need... But there's no restriction on a, it's just any positive real. Maybe I should get the cas out. Do these a bit better. Oh, right, the reason I didn't do it is because you can't get g inverse on it. Now we can plug in the two numbers anyway. The whole x equals 2a on 3. You can do that via the relation menu. 2a on 3. Then x equals 3 on a, which should be all the way out at x equals 3 if I'm calculating that right. So I don't quite know how that's possible, considering we're only allowed to be from 0 to 2a on 3. A being a positive real. Which one is a positive real? And yes, if we do increase the size of A, yes, they are eventually going to swap places, but not always. That's a bit strange. Only one of those actually fits in a domain. I mean, area bound by G inverse, x-axis, and this line. The way to go about that, because we can't get our G inverse, I did kind of just go on a bit of a tangent there. It doesn't really matter too much because we can't get G inverse, so we're going to have to do something with G, which effectively means swapping all these x's for y's. So instead of saying G inverse x-axis and x equals that, we say G y-axis and y equals that. So that's what we're going to do anyway, with this result notwithstanding. So basically, killing both of those. Can I just do that? Yeah, I can. Making them y's instead, and then comparing that to the G. So from there, I want to get rid of F2 as well, actually. And from there, we're now doing tab. So it was y-axis and g of 2a on 3, g of 2a on 3. That's just going to end up being that bit in there. Which, now that we're seeing it, that's pretty chill. Which brings us to why D was important. 2a on 3 times g of 2a on 3. That will be like saying, hey, this distance horizontally from here to here, this x coordinate of that turning point was 2a on 3. The height is g of 2a on 3. So in other words, doing that evaluation in part D gave us the entire box. From there, there's a couple ways we can take it. We could just do the integral of the blue line and then subtract that from the answer to D. Or we could ignore that entirely and just say, yep, top take bottom, this one minus this one from 0 to 2a on 3. So that tangent was sort of whatever. It was a bit weird, but fundamentally didn't really matter that much. We couldn't find G inverse, so we got to get things in terms of G. Just be aware that actually this one's also the same, which is it doesn't say in terms of A, so the A probably cancels itself out once more. Let's explore that. So we had it earlier from here. The result is 2, and we're going to then subtract the integral from 0 to 2a on 3 of whether it's G or F, it's the same thing. And it's going to give us 1. Alternatively, if we play it a bit safer, kill the A, still cancels itself out. I'd be surprised if this had a decent pass rate. There it is, 7%. Nice. I wonder if they were also playing with the same stuff I was and then just sort of threw their hands up and was like, nah, not dealing with this. When in reality, like, I just thought I overcomplicated things. If you can't find G inverse, or if it's not particularly easy to find G inverse, then you can always just work with G and then swap every instance of X with Y, which is how we're able to do that. It's going to be about it, really. Got about 30 seconds to spare. Anything in there worth clarifying further?
That's it. Bye, Chris.
No worries. Take care.
See you. Bye-bye.
Bye.